do, and I will fix that. I have the thermostat as high as it will go. I've been told that it has something to do with they just turned off the phone system.
Change the sign of
Exactly. And yeah. I apologize profusely about I think I'm getting a cold from it.
Thank you. It's a pleasure to come back to my alma mater and give a few lectures. Always nice to come back and see our stage. I was thinking beforehand, what do I have time to talk about in a relatively short amount of time, and asked a little bit around and got some advice. And the advice was that one of the most useful things I could do would be to sort of give sort of a broad overview that would cover things not necessarily that I'm working on everything, but I have worked on a lot of things over the years, and so I have this sort of broad perspective that not so many people have. And so one of the most important things, for instance, in starting out in your research is if you have a problem, which method should you use? And so you sort of need, I was told, well, Cornell students are smart, which, I was here, I agree. But they can figure out the method, but how do they know which one to work on? So this is designed this first lecture is designed to give a bit of an overview. And it's a sort of an overview of numerical methods for strongly correlated systems. It's of course biased because I only worked on a subset. There's so many methods that I'm just sort of biased towards the ones that I've worked on or the ones that I like. But presumably that's useful also. And so I'll try to give you some sort of perspective on this. So first I'm going to start off by framing the problem in terms of the different types of methods, and you can, one axis that you can choose to characterize them is how exact they are. And so I'll talk about that, and then talk about some particular methods that sort of comprise the overview, starting with exact diagonalization, which still is often very useful. And then talk a little bit about quantum Monte Carlo, in particular the determinantal type of quantum Monte Carlo that Era's mentioned, I talked about in the last talk, and then also a variation of that controls the sign problem called the constraint path method. And then talk about the closer to home for me are the low entanglement method. We now understand DMRG as being the key idea that makes it work is low entanglement. And so I'll talk about how what that means to have low entanglement and this general class of methods. Another recent method that can be framed that way, an Empyrean method, is this density matrix embedding theory. I'll say a little bit about that, and then also about the two-dimensional tensor networks, and try to give a sort of brief overview of everything. And one of the interesting things that those of us working in this have decided, many of us have decided that it's very useful to use more than one method at once. You have strengths and weaknesses for each method, and so it's nice to have a collaborator who can put their strengths where your weaknesses are, and vice versa. And so I'll show some results that we've been doing associated with the Simon's collaboration on the many electron problem. Okay, so first of all, just to sort of try to give the broadest possible view, there are numerical approaches for condensed matter systems, many electron systems. There's lots of good approaches, and they're good in the sense that for some class of problems, a lot of people use them because they don't see anything else that will work better for their particular